Welcome back to Let's Code. I'm Chris Biscardi, and today we are going to investigate building Flappy Bird inside of Bevy. So if you don't know what Flappy Bird is, I'm just going to play a game right now so that we can see. You basically can click, and when you hit the pipe, it's game over. And it's really hard to play and talk, I've discovered. But basically it's click, 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 click. Every time you get through a pipe, you get a point. And then eventually you kind of fail at it and you hit the ground or a pipe or something else and the game's over. So today I started working on what that might look like in Bevy. You can see an extremely slow version that I've kind of zoomed out for here. We need a sensor. So I've decided to use, first of all, Bevy Rapier 2D for a lot of the collision detection and sensors and things like that. So you can see here a collider for a pipe on the top, a collider for a pipe on the bottom, a collider for the ground on the ground, and then this sensor on the left-hand side that whenever this pipe collides with it, or more accurately, I think it's the sensor in the middle right now, it resets and comes through for another time. Now, this is not the full game. This is obviously a prototype. But we're going to go through what this looks like. And I am clicking the cursor for the Corgi the entire time I'm doing this. So you'll notice a lot of the physics, a lot of the movement of the pipes, a lot of the speeds are not the same as the game that we just played. And that's because I'm using this for development purposes, and we'll fine tune the gameplay when it's time to fine tune the gameplay. So if I play this on a more reasonable screen size, you can see that the collider that the pipe runs into and then resets happens on the left-hand side of the screen. It's not actually on the screen. I just wanted to show it. And we also have not implemented yet scoring. So when I go through the middle, you'll see that the Corgi triggers the sensor up in the logs, but it does not actually increment any points yet. And if we touch the pipes or touch the ground, the Corgi does not actually send a game over or go flying or anything. There's work to do, but I think this is a pretty decent prototype, and it gives me a little bit of a talking point to go into what's actually going on here. So in this case, I have a Corgi.png that is a 12-step sprite. This is the same Corgi I use everywhere, so if you've seen it, this is what it is. We are using Bevy Asset Loader to pull in the Corgi PNG into a texture atlas. And I've also included Bevy Cura Audio, which we are not currently using, and Bevy Rapier 2D with an optimization level of 3 when we build so that the physics runs appropriately. So let's dig into this. We have Floppy Corgi for the window description. I set the default width and height to 1200 by 600, although the way that I'm coding this Flappy Bird implementation is that it sort of expands to the size of the window dynamically, almost like you would expect a media query in CSS to do. So if I ran this on a phone, it should fit in a 9 by 16 area. If you run it on a desktop full screen, it should blow out to that size, and you should just be able to see more pipes basically. So the window size isn't terribly important. Then we've got the default plugins, which, the default plugins in Bevy let us do all of the things we like Bevy to do. And here we've got a couple loading states. You'll see my states here is a direct rip from the Bevy Asset Loader full collection example, if I remember correctly. So one of the things that I like to do when I'm getting started with a new project is take one of the pieces of infrastructure that I'm going to use that has the most setup code associated with it and go to the examples directory inside of that GitHub repo and choose one that I feel like using. Now, Stageless is compatibility with IES Loopless, which I've decided to not use yet. I don't have progress tracking for loading the assets in since I really only have one asset right now, and it's kind of a prototype. So the one that I went with is the full collection. In this case, it is the default plugins, and then this loading state struct. This struct has two states, asset loading and next. Next is when the game plays. So we add a loading state, we set the state to assets loading, and then after the assets are all loaded, we continue to my states next, and we use the my assets collection as the thing or set of items that we need to load to move to the next state. And then we add the my states asset loading state as the initial state for the game. And when we enter, so system set on enter, the next state, we run, in this case, the expectations system. But in our case, this is actually just the setup system. So it sets up the camera and the sprites and things like that. In addition to Bevy Asset Loader, which actually let's cover this for Bevy Asset Loader first. Bevy Asset Loader has this asset collection derived for a struct. In this case, we specify the path as being this Corgi PNG, which is in the assets directory by default. And we specify that Corgi is going to be a handle to a texture atlas. We're using a texture atlas because we're going to animate each of the steps for the Corgi to make it look like it's, running or swimming or whatever, flying or whatever. Bevy Asset Loader has native support for texture atlas, but note that you need to enable the 2D feature on the crate if you're going to use this. So it has native support for texture atlas with this attribute macro. We specify the tile size X, the tile size Y, the number of columns, and the number of rows. So in this case, it is 500 by 500, which means it's 6,000 by 500 with 12 items in a row. So we also use the Rapier physics plugin and the debug plugin renderer, the debug render plug, the Rapier debug render plugin. I'm leaving the Rapier debug render plugin in here because it really helps when setting up all of the colliders for the first time and things like that. I usually do all of my development with these colliders on, which sometimes leads to me not specifying colors for my sprite, but that's a me problem. We've got a number of systems here. We'll go through them one by one, but all of the systems are added to always run. We've also got a number of components at the top. So we've got the Corgi that we're going to be controlling. Every time we click, the Corgi gets a force upward. And when we don't click, gravity pulls it down. We've got the ground. So if the Corgi collides with the ground, it's going to signal a game over. If a pipe hits the pipe despawn area, which is a rectangle, then it will reset or trigger the spawning of a new pipe. In this case, a pipe is a spawned bundle made up of 3 sub items or 3 sub colliders. So there's the top pipe, the bottom pipe, and the point skate or the little green thing in the middle. So just go over those again. There's the top pipe, the bottom pipe, and this green sort of sensor that just triggered in the middle. The green one on the bottom is the ground, and then the one off screen to the left is the pipe despawn area. Our setup function runs after our assets have loaded, so we get to access our assets through a resource. We can do res my assets. And remember, this just has the Corgi PNG in it. We also grab the window because, like I said before, I'm trying to make this kind of a responsive game. So we need the dimensions of the window to be able to place all these objects on the screen in the right places at the right sizes. The Windows asset has a primary function that will get us the primary window. I don't plan on spawning any other windows, so this should get us the only window that is around. And then we spawn in a 2D camera bundle. Again, in Bevy 0.8, we've got these camera 2D bundles instead of the orthographic camera bundle. Not a huge change there. The sprite size is set to 100, which is interesting because our physics pixels per meter is also set to 100. What this means is that 100 pixels is roughly equal to 1 meter, which means that our Corgi actually is, as we'll find out later, 1 meter tall, which seems like a lot for a Corgi. Maybe I'll make that smaller in the future. So we take our texture atlas from the assets and we clone the handle in. So a texture atlas, again, is this basically set up so that it has multiple indexes. So index 0 will be this first one, 1, 2, 3, 4, 5, 6, and so on. This allows us to change the actual image that we're using without loading in a completely new image and inserting it into the sprite. We want to put this Corgi at sort of like 1/4 into the screen. Again, we're doing a kind of a responsive game here, so I've chosen to do this off of the window width. Because 0, 0 is in the center of the screen, that means if we divide the window width by 4 and then subtract it, so we get a negative value here, we move 1/4 of the screen backwards from the middle of the screen, which puts us 1/4 into the horizontal x-axis of the screen. And then our y, for the same reason, is set to 0 because that puts us right in the middle of the screen. And the z-index is 1. Z-index is, actually, I don't remember if Bevy calls it z-index. I might be just reusing my CSS knowledge. So this is basically layering. So a higher z number will put that sprite in front of another sprite that might have a lower z number. In this case, I've just specified 1. When I have everything set up the way that I want to, I will probably put the ground in front of the pipes and then make sure that all of the z-indexes are set appropriately. Then we set our texture atlas sprite as the sprite in the sprite sheet bundle. We need to flip the X because if you look at the Corgi, it's facing to the left in this GIF or this sprite sheet. So we need it to face to the right. And then the custom size is the sprite size. This custom size is changing the 500 by 500 default that this Corgi happens to be, and it's squashing it by 1/5. Doing the custom size here instead of doing the custom size in the transform using, say, a scale or something, means that when we insert the collider, which is a cuboid, we get to just divide the sprite size by 2 and have it work instead of having to do additional math to scale down the sprite while scaling up the cuboid or something like that. We do insert this animation timer. This animation timer is a custom struct, embeds a timer that fires every 0.1 second. If we look at this animation timer, you can see that it takes a timer and we derive component and deref and deref mute, which are some convenience functions that Bevy gives us, or convenience derive macros that Bevy gives. The animate sprite function runs all the time. We get the time resource from Bevy. We don't use it ourselves. We don't get it ourselves because Bevy controls the time. And that's just like, if you're going to use time inside of a game, get it from Bevy. Don't make it up yourself, or don't get it from like the system clock or something. In the animate sprite system, we get all of the texture atlas resources. So we get the texture atlas resource database basically. And then we query for any component that has the animation timer, a texture atlas sprite, and a handle to a texture atlas. We can loop over each of those values in the query, and we can destructure them into their own variable names. So in this case, we've got a mutable timer name, a mutable sprite, and then the texture atlas handle. We do some timer logic, and then if the timer just finished, we then get the texture atlas handle, and we set the sprite index to the current sprite index +1, which is modded by the length of the number of textures in the texture atlas. So the math here is saying basically we have 12 of these or 11 of these, or depending on whether you're 1 or 0 indexed here. We're going to be 0 indexed for the purposes of this calculation. So the length is going to be 12. But if we do, say, if we're at sprite index 0 and we need to move to the next index, we move to sprite index 1. If we move from sprite index, say, 12, or move from sprite index 11 +1 to 12, then we mod it by the length of the number of textures. So 12 mod 12 is going to give us 0 because 12 is divided by 12 evenly with no leftover numbers. So that's all this is doing, is making sure that we have a digit from 0 to 11 rather than an ever incrementing number. And this is the reason that the Corgi animates. So we're basically just bumping up this index over and over and over. The Corgi itself is a dynamic rigid body with a velocity of 0. We've already gone over the cuboid collider size. So that's, each of these numbers is a half extent, which is a weird name. But what it means is it's basically half of the height of the actual side of the cube. So, or not a cube, rectangle in this case. So if we have, say, the left-hand side of the cube, the entire length is sprite size, but half of the length, or the half extent, is 1/2 of that. So Rapier does this way. Bevy does it the other way. So Bevy will just take the entire length of the side. So that's important to know and not get tripped up by. Of course, we don't want the Corgi to rotate, so we lock the axes using the locked axes rotation locked. And we insert the external impulse, although we start it at 0. So there is no torque impulse, there's no rotation, and there's no XY impulse in a direction at all either. But we need to insert this so that we can modify it later. And when it gets modified, Rapier will then make our thing jump or something like that. I also increased the gravity scale a little bit. This is a number that we're going to have to play with because in the original Flappy Bird, the up and down is kind of very drastic. So if we look at how fast this goes up and down, it's kind of not very realistic, or it's faster than what we have currently anyway. So I bumped up the scale a little bit. You can bump up the scale on any of your colliders or any rigid body that you have in your system for Rapier, which is really nice. We insert the Corgi component so that we can query for this later, and then enable active collision events. And this is really important because at some point we are going to have to, in this system right here, the display events system, we are going to have to detect when the Corgi hits anything. If the Corgi hits a sensor, then we increase 1 to the score. If it hits anything else, we end the game immediately. So that's why you can see that on the left-hand side here. If I open this up a little bit and run the game again, anytime this touches, say, the ground or the sensor, or maybe the ground again, we get this started, stopped, etc. So in the case of it being a sensor, like the one in between the pipes, we get this sensor property. When it is not a sensor, that is empty, but we'll deal with that when we deal with that. So this is just reading the collision events, and to read the collision events for the Corgi, we do have to enable the active collision events with this component. Each of the next items is maybe a little bit of placement math, but overall the same thing. We get the window width and the window height. I've chosen to specify fractions of the screen width for the size of things like the ground height or the size of the sensor to the left of the screen. So that's what I'm doing here. I'm just saying the ground is going to be 1/10 of the height of the screen, whether we're playing on a phone or we're playing on a desktop. And the ground actually is one of the systems that has sort of reactivity built in. So if I make this bigger, you can see that the ground gets bigger. If I make the window smaller, you can see the ground gets smaller. It's always going to be 1/10 of the height. You can see that I haven't applied the same logic yet to the despawn area on the left, because the despawn area on the left will just sit there. So we set the size in the same way we did before. We set the ground size .x and y for the sprite. We set a color. We use a sprite bundle. In this case, I'm putting it at, remember, the point in the middle of the screen is 0, 0. So -half of the height of the window plus the ground size over 2. So we're putting it all the way at the bottom. We're putting the center. One other really important note is that the anchor, the position at which we are positioning all of these things on screen, is the center of the square that we've created. So we are putting the center of the box at the bottom of the screen here. The box is actually double the height, so we need to add a little bit or half the height back so that it sits at the bottom of the screen and is a full 1/10 of the screen. The ground is a fixed rigid body. There's a couple of different rigid bodies, dynamic, fixed, and 2 kinematic. And we do the same thing here, and we insert the ground component. The pipe despawn area is exactly the same thing, except we're doing half of the width off the screen to the left, and then we're subtracting the width of a pipe again, so the pipe can get fully off the screen to the left before it resets, and we initialize a new pipe on the right-hand side. The pipes itself is interesting. This is something that I'm going to pull into its own custom command, I think, because we've got the new spatial bundle here. So we are spawning the spatial bundle, which gives us a transform, a visibility, and a global transform. We're inserting a rigid body, kinematic velocity based. We're inserting a linear velocity. So Rapier is handling the movement of a pipe from the right to the left constantly. It is always going to be moving left at -100. And of course, we can change this velocity at any given time. So if we wanted to, we could loop over all the pipes and speed them up over time to make the game a little bit more difficult as you stay alive longer. Now, this gives us a root entity through which to contain the rest of the pipes. So you can think of this as almost like a container div, if you're familiar with web development. At the top, we've got the top pipe, then we've got the gap sensor, and then we've got the bottom pipe. The top and the bottom pipe are basically the same thing, so I'll just go over the one here. It's a sprite bundle, set the sprite to a sea green. The pipe size has an X and a Y, which we set up here. The pipe size is always 200 width, but it's always half the height as well. We do half the height so that the pipe can sort of stay off of the screen, if that makes sense. So we've got a pipe that goes up to and a little bit past the top of the screen, and a pipe on the bottom that goes up to and a little bit past the bottom of the screen. We set a cuboid collider again. We set the active collision events, and then we insert a component pipe top. Now, this is the exact same thing we do for the bottom pipe, so I won't cover that. But the middle of it is this gap sensor, and the gap sensor is a specific size. So what we do here is this transform is relative to the parent. So the center of the parent is going to be the center here. So we can set this gap sensor, this score sensor between the pipes to 0, 0, and whatever size it's going to be, it will sit right in the middle at 0, 0. And then we can move the top and the bottom pipe, or the top and the bottom pipe around it, which is what we do right here. So we take the pipe size .y over 2, which is we do the pipe size over 2 because we need to be moving the center point, not moving the top edge or something like that. And then we subtract the gap size over 2 to move the bottom pipe down half of the size of the gap and the top pipe up half the size of the gap. And that's mostly it. So all we've got left is the Corgi control, which is almost a one-liner. We get the input for the mouse button, and we query that external impulse we talked about earlier that the Corgi has. And if we press the left or the right mouse button, then we take the Corgi, we get the impulse value on the external impulse, and we set it to positive 200 in the Y direction. So the Corgi goes up, and then we let gravity take care of taking it down. So that's the entire movement code. When you click the button, it goes up. Align to window is a little bit more interesting. It's the thing that reorganizes all of the colliders and the positions of the ground and things like that when the window changes. So we have to get the windows in the query. We grab the Corgi with the transform, and we grab the ground with a couple of items that we're going to change. We only run this function if the window size has changed, so we don't have to constantly deal with the performance impact of constantly setting all of these things all of the time and as fast as the system can run. We get the primary window, and for the Corgi, we set the Corgi to, again, -1/4, which, because 0 is in the center of the screen, makes it on the left quarter of the screen. And then for the ground, you can see that I'm looping over both of these, even though there's only one Corgi and only one ground. That's because I'm running these systems all of the time. And if there isn't a Corgi or there isn't ground spawned in yet, then these for loops won't run. And if they are spawned in, then they will run. And that kind of is a little bit of resilience that I'm building in here, even though there will only be one Corgi and there will only be one ground at a given time. So this is doing the exact same thing. We set the position of the ground and the size of the ground in the same way we did in the setup function. We're just doing that every time the window changes here. We talked about the collision events already and the event reader that we have because of that. And then the very last function that we've written is display intersection info. Now, the big issue here is that in Rapier, the sensors on the screen don't intersect with kinematic velocity-based rigid bodies. So they won't be, we have this collider event reader here, but a sensor and a kinematic rigid body will not be in this event list. Where they will be is in this intersection query. So we query for all of the gates, so all of the pieces in the middle of all of the pipes. We query for all of the pipes themselves, so the whole thing together, not any individual piece. We query for the pipe despawn area off the left-hand side of the screen, and then we grab the Rapier context. For each of the gates in the pipe, we grab the despawn area as a single, and then if the Rapier context tells us that the gate that we're querying right now and the despawn area are intersecting, then what we do is we get the pipe from the pipes query. So you can, on any query, you can do a get with the entity ID for the query, and it will give you back the component that matches that entity ID, which is a little bit mind-boggling when you see it the first time, but it's really, really cool. And it was one of the things that allows us to run a couple of queries and not have to build up really, really complicated queries. We can query for, say, all of the transforms, or in this case, all of the pipes on the screen. And then we can get just the one we need because we have access to the entity ID from a different query. And then because that gives us the transform and it's mutable, we get the translation, we set it to 500, and that's what gives us the loop. So that's it. It's just a prototype. It's not too much code. You can see every time the Corgi hits the sensor, it triggers. Then when there's an intersecting collider, the pipe gets reset, and so on and so forth. And we don't have scoring, or we don't have game over yet, but we do have collision with everything we need to have collision with. And we can get to kind of making some nicer visuals and getting the game feeling like it should. One of the other things that I want to do with this game specifically that I've already got set up is I want to specify the center of the opening based on a noise function so that we can determine whether the change in the center position from pipe to pipe should be gradual or it should be much faster. So that'll be interesting. A lot of work to do here, but this is, like 400 lines of code. I think the only thing that I really got hung up on here is that Rapier doesn't trigger collisions or doesn't submit active intersections for sensors and kinematic rigid bodies, which I found really weird, but apparently this is pretty standard. So I don't know. I haven't found too many people talking about that specifically. But if you know something about why sensors and kinematic velocity rigid bodies don't trigger collisions or don't trigger intersections, let me know in the comments, because I'm curious and I can't find anything on it. But in the meantime, I have used this intersection pair query to deal with that problem. I'm doing it the same way in the block breaker game. So that I find really interesting because it feels very non-obvious to me. We've got this nice little prototype and we'll build this out over the course of the next week or so. And hopefully I will get this up on the web for y'all to play, because this should work just fine on the internet. And then maybe we'll also do, I've been wanting to do an iOS game, or at least try to compile Bevy to iOS. So I think that this is a really good candidate for trying to do that and sort of debugging some of the issues that come along with that. I do need to do that on actual iOS hardware. So I need to get my stuff together and make sure that my iOS device works. I hope you enjoyed this brief look into Floppy Corgi is what I'm calling it. But I hope you enjoyed this brief look into Floppy Corgi, a Flappy Bird clone in Bevy. And hopefully we'll get some of these controls feeling a little bit better, because right now it feels very like these gaps are way too big. And when I click, it doesn't really move like I would want it to move. It's a little bit too controllable, I think. I can just kind of like bump it along here and keep it at basically the same height. Whereas a lot of the challenge in the original Flappy Bird is that it goes up like that and then all the way down, and it does it a lot faster. So work to do, but super happy with how far I got with this prototype. It didn't take me all that long, and I will catch you in the next video.